Okay, this lesson is on productivity. So productivity is basically how much energy is transferred from one trophic level or layer of the food chain to the next. And we're going to look at, first of all, we're going to look at plants. So we're going to call it primary productivity or production, depending on your exam board. I'll explain which people need to use which words in a moment. So let's get all fancy and use a ruler. Okay, so start off with nice and wide and do a full line, why not? Okay, so this is the total amount of energy that's made by the producer, and we call that the gross primary production if you do AQA, which is a bit weird, or productivity if you're everybody else. So this is GPP, gross primary production or productivity. Most people call this productivity. I'm sure AQA students are not going to get marked down for calling it that. I will maybe just put production and just put AQA in brackets. It's always been known as gross primary productivity as far as I'm concerned. I'll give you a little definition of what we mean by that. So this is the total amount of energy made by producers, and the units are given per unit area per unit time. So the units are given. I'm going to probably do these in black to make them stand out a little bit. Let's say, for example, we're going to use nice round numbers to begin with. This is 100,000 small k big J kilojoules per meter squared per year. Again, we need to include the time because this is going to change throughout the year, if it's summer or if it's winter, etc., etc. And now this is made up of different components. So let's divide this. Given my numbers, my divide needs to probably go about there. So some of this energy is used by the plant, funnily enough. It's going to have some metabolism. It's going to do some metabolic processes. So this we're going to call R, which is respiratory loss. And I'm going to put some hypothetical numbers in here. Let's say this is going to be 40,000, and the units need to be the same, kilojoules per meter squared per year. And that leaves the rest of the energy that the plant doesn't use directly for things like active transport and stuff like that is going to be the net primary production or productivity, and that's biomass. How much does it actually build in biomass each year? Here I'm just going to write NPP. In fact, that is a recognized shorthand. I'm going to add GPP up here. I'm going to define that underneath. So net primary production or productivity is basically the biomass that it accumulates during that time. So for this, I could give you an example. Well, this is always going to add to the same. And this is 100, nice round number. This is 40,000. Well, to calculate net primary production, we're going to look at the sum later on, but it doesn't take a genius to work out. You take the total, you minus what's not converted to biomass, what's used effectively, and we end up with the balance, which is going to, in this case, be 60,000 kilojoules meter squared per year. Okay, so let's define net primary production or net primary productivity. So production, AQA, productivity, everybody else. So this is the amount of chemical energy that a producer, because it's primary, it's the producer, stores as biomass. And again, the units are per unit area, per unit time. This is also per unit area, per unit time. Which means our units are kilojoules per meter squared per year. So let's add a little extra note on that. This is the total amount of energy that's available to the next trophic level, the next layer of the food chain. That if I wanted to eat this plant, I can't access this energy because it's already been used by the plant. So this is the only energy that's available to me if I'm a consumer that I want to eat the plant. I'm going to put trophic level in red. Troph means like nutritional, basically. So autotrophs are self-nourishing. Trophic, that's supposed to be a pH, not very clear. level, which means the next stage of the food chain. Okay, so if that's the total amount, what I'm actually going to do is, I've started with a ruler, I probably should continue now, shouldn't I? So let's take this, and I can draw a dotted line down here, and also the same on the other side. And this is going to continue down to the next trophic level. So let's say a consumer comes along and eats this plant. Now, it's not going to necessarily eat all of the plant. So this plant may have deep roots. It obviously can't access every single bit of every part of the root. So some of the organism, and this is true whenever you have a gap between trophic levels, so not all of the plant is eaten. I'm going to call this, this is an unofficial shorthand. I'm going to call this X here, and I'll come back to that in a moment. So this is the total, this would be effectively the gross, the equivalent of the gross primary productivity. We can't call it that because this is not the primary, it's not a producer, it's not the first step of the food chain. So this is the total amount of food that's ingested by the consumer. So this is known as I, and I is the total food energy ingested. Total energy in, you can think of it. So opposite of egestion is ingestion, food going in, like immigration and emigration. So let's maybe give this another hypothetical number. Well, this is 60,000 total. Some of it's not being consumed. Let's call it 49,000. Units are the same. And again, so this is the total amount of energy taken in. What's this consumer going to do? Well, a fair bit of this is going to be respired. So similar story. I'm going to have I'm going to define respiratory loss, so I'm not going to add anything else there. Let's say in this case we're going to call it 35,500. I might start getting a bit tight on space. And then we've got one other thing that animals do that plants don't. They shit. They excrete much more, and so let's go with a divider in here, and this is going to be F for feces. I'm going to put that down here. Feces and urine, technically. And let's say, for example, so it's undigested food. Let's say this one, 8,100. Okay, and then lastly, we have what the consumers convert to their biomass, and this we're just going to call N. And N is going to be net production or net productivity of the consumer. So that we don't say the primary here because it's not a plant. Again, I'll just remind you that production is for AQA. I very much doubt they're going to mark you down if you use the wrong one of these terms. It's just good to know. Now, how do we calculate this? Well, again, much the same way that we calculated the net primary production. I'm going to do the sums over on the side, and we're going to calculate what this is. Assuming we've got these data points, yeah, we can figure out what that's going to be. So let's write the equation down the bottom here. So net production is equal to the total amount of food ingested, which is represented by I, minus the losses from the system. And the losses from the system are respiratory loss and loss from feces and urine. So how could we calculate it in this case? Well, let's look at some numbers for that. In fact, let's define respiratory loss, so it's all nice and tidy. Yeah, respiratory loss is the energy used by organisms for respiration. So I'm going to give some examples here. Remember, plants respire too. Plants are respiring all the time. Everything needs ATP. Everything needs to respire. So this could be for plants, for example, could be active transport. If it's a mobile organism, if it's a consumer, then it could be muscle contraction. It could be could be lost as heat. Especially, you can call them homeotherms or endotherms, warm-blooded, things like that. Okay, so now we know what respiratory loss is. Now we can look at the numbers for calculating net production. and net productivity. In fact, let's do both the equations. Let's do net primary productivity. So this is looking at these numbers here. Well, what's the equation there? It's gross primary productivity, or production, minus the respiratory loss. I'm not even going to run through the numbers on this one. We've got 100,000 minus 40,000 gives us our 60,000 if we want to work it out. That isn't going to be too difficult. Calculating the efficiency of energy transfer. Well, these numbers are quite straightforward, which is why I've chosen them. This is 60% efficient. What percentage of the total energy ends up as biomass is what we're trying to work out. And this one is clearly, we've got 100 and we've got 60, so it's 60% efficient. Now we're going to use these numbers to calculate the percentage energy efficiency for the consumer in this cycle. So let's look at how we're going to do that. We've calculated now that from these sums, well, in fact, what I'm going to do, I would always use a calculator during these equations. So let's work out net production first of all. So total is 49,000, and we need to remove what's taken out of the system. So respiratory loss is 35,500. And then we can also remove what's lost from feces, which is here, 8,100. So that gives us we can calculate from that our net production is 5,400. Again, units always the same. Okay, so now we've worked that out. So now we want to know what percentage is this of the total, which is going to be I, which is our 49,000. Okay, so we can calculate this by taking these numbers here. And how do we calculate the percentage of this in here? First of all, you've got to stop and think. What we've looked at energy transfer through ecosystems. We can look at this diagrammatically. This is as a percentage of this. Well, roughly what's it going to be? Always have a think about what it's going to be first. If your percentage energy efficiency is more than 100% when you've done your calculation, you know that you're wrong. You cannot eat an apple and gain the weight of 2 apples. It's just not possible. Energy is lost along the way. So this number we're looking for to be roughly 10%, depending on the ecosystem, the food chain that we're looking at. So just every time you do a calculation in your biology exam, do a quick, very round numbers. This is roughly 50,000. This is roughly 5,000. Well, I'm looking for, again, roughly 10%. That's corroborated by these numbers. Have an idea of what it kind of should be, because then if you make a mistake, you get your denominator and your numerator the wrong way around, and you do your sum upside down or backwards, and it's wrong. It should become obvious to you. So, okay, let's look at this. We want to know, we're going to take the net production. Let's put a little subtitle. This is calculating the energy efficiency. And to do this, we're going to take the net production. We're going to divide it by the total energy that's gone into the system, which is I. And we're going to times this number by 100 to get a percentage. So let's look at these numbers. In this example, we're going to have 5,400. We're going to divide it by a total of 49,000. And then we're going to times this whole thing by 100. So let's see what that comes out as. I would always use a calculator because it's very easy to make simple mistakes. Times by 100 gives us 11%. Is it just over 10%? Yes, it is. Does that make sense? Yes, it is. Does it make sense for the food chain? Yes, it does. Okay, so we're quite happy with that. I might even write this number down. So before we times it by 100, we worked it out as being, again, don't make silly mistakes, especially when you're on camera, 0.11020. If I'm writing down an intermediate number in a calculation, I'm always going to write it down to more significant figures than I need to, because if we're then going to take this number, 020, I'm going to times this by 100 to get our percentage. So in the exam here, this is a 0, which makes our life nice and easy. I think 2 decimal places, 3 significant figures. Always use what they've used in the question. If they've given data to 2 significant figures or to 4 decimal places, use what they've done in the question. If in doubt, this isn't going to get you into trouble. So 2 decimal places, 3 significant figures is a pretty good benchmark as what you should be using. And that gives us our percentage transfer of 11%.